So this morning I'm going to talk about the work that we've been doing to develop the next standard configuration for standalone JULES. So JULES, the land surface model that's used within the unified model. We're going to be using a benchmarking system based on the modelevaluation.org. So first, a few fundamental questions. So what is benchmarking? So the land surface modeling community has been developing a kind of growing understanding of what the difference is between evaluation, comparison, and benchmarking. So this example has come from this paper written in 2015 by Best et al. So in this example, we compare evaluation is basically a model compared with observations to develop an error measure. Comparison basically is where we compare two models, so model A and model B, and the error measures between the two. And we get a comparison between the two models. But what does this really tell us? So benchmarking is a completely different approach where we actually define what we want to achieve, so what our performance we want to actually aim towards before we run our simulations. So in this case, we've got model, where's the mouse gone? There we go. So model A and model B, compare with the benchmark in green, and it gives us a completely different result. So in this case, both models actually outperform the benchmark. Model A is obviously slightly better than model B, but both models are actually genuine results. So the idea is that you define your performance that you want to actually aim towards before you run your model simulations. So there's three different types of benchmark we want to consider. So first of all, is it better than another model? So in this case, we could use another model as a previous model configuration or a completely modeled from the start. So the second type is it fit for a particular application? So we're looking at particular impacts. Does it actually do what we want it to do? Does it generate the right processes? And thirdly, can we effectively utilize the information that we've got available? So if we give a land surface model the correct vegetation or the correct soil, it should outperform a model that doesn't have that information. So in this work that we're doing, we're looking at whether the JULES configurations actually outperforms the previous model configuration. So if we add new science to the configuration, does it actually outperform what we'd had before? So we're using this in order to develop new configurations for JULES, particularly on the standalone basis rather than the coupled. So moving on to another fundamental question, so what is a configuration? So we defined it as a collection of settings, switches, and parameter values that we use to define the scientific setup of the model. And a configuration is not the driving data. It should be resolution independent. It shouldn't include the ancillary files, although the method we use to generate them can be included within a configuration. It shouldn't be application dependent, and these are all part of the experiment and not the configuration. So the aim here is to create standard configurations that give the best simulation of the physical and Earth environment, and we demonstrate this by using predefined benchmarks. So for the configurations for JULES and the we have several coupled JULES Unified Model System configurations, which Rich has mentioned, which is the GAL and the RAL. We also have the Earth System Model, the UKSM. So the GAL and the RAL underpin the weather and climate models. They basically are globally applicable. They should be the best configuration for simulating heat, energy, and water fluxes globally. The UKSM will build on this and include interactive carbon, nitrogen cycles, methane, and this is basically the best configuration we have for understanding the Earth system and the carbon cycle. So for this particular example, we're looking at standalone JULES. We require configurations for both the physical land and the Earth system land in this case. So we've chosen to use the modelevaluation.org application to generate a benchmarking system. So this, for those of you who don't know much about the ME.org, is a community-based web environment that allows users to download a set of driving data sets from 170 sites globally. Basically, you provide the daily meteorology downloaded from the site, along with a wide variety of different parameters that are required for the land surface model, such as the vegetation and things like the canopy height and that sort of thing. So the model output is then the models actually run with this data, and the output is then re-uploaded back to the web application and analysed using the scripts and the analysis that's available on there. So with this, we have the benefit of being able to compare our model with other people doing the same thing. So there's many other ACCESS models available there. There are other benchmarks available there other than just the benchmarks we're using ourselves. So there's empirical benchmarks. There's also an extensive different range of different metrics and statistics available. And essentially, we're generating a consistent, reliable, and robust set of runs that we can then compare against the rest of the community. So this is the process that we've set up. So what we've done is we've taken the ME.org, we've actually developed our own suite using the ROSE system. So we run all our own model runs offline using all the data that we provided from the ME.org. We convert this into JULES inputs and run a ROSE suite for every single site, it's 170 sites. From this, we're able to calculate the output metrics. So we compare JULES versus observations for every site, for every variable of interest, for every configuration and every benchmark. And then we do some analysis. So the benchmarks that we're using for our application here are a number of flavors of the global land system. So in this case, GL8, GL8.1, GL9, and GL9. Each have very specific science configurations and different things that have been added in kind of a sequential sort of time sort of way. So GL9 is actually the most latest, effectively the cutting edge configuration we have for standalone at the moment. So we want to beat that. So this is just a bit of a summary of the analysis that we've done. So we've compared JULES versus the observations for every site, for every variable, for every model configuration, every benchmark. There's 10 statistical metrics, 6 different variables, including latent and sensible heat flux, 4 benchmarks, and they say 1 new model configuration, which is this new package that we've developed. So the metric values have basically been ranked from 1 to 5, so every metric that's calculated for every model observation comparison. These rankings are then averaged over all statistics at all sites to give an average ranking for all the variables separately. And then we've done a final averaging of all the variables to give an overall ranking. And this basically allows us to have a single plot that we can compare with a single dot, so we can see exactly what our new model configuration is doing in the range of benchmarks that we've got. So these are the summary plots that we've generated for the physical land package. So on the left-hand side, we have the average rank over pretty much everything, so the metrics, variables, and sites. And the black dot is basically our new package, and blue, red, green, and yellow are the individual benchmarks. So the lower the rank, the better the configuration, and the error bars are 95% confidence intervals. So in this case, the new package outperforms, on average, across everything, all the benchmarks, which is really good to know. If we subdivide that into the individual variables, so here we have the long wave up, the latent heat flux, sensible heat flux, net radiation, GPP, and momentum flux. And in every case, the new package outperforms the existing benchmarks, apart from for the sensible heat flux. Now, this is the case where we've added new science, and we managed to narrow it down to a particular change that we've made to the surface albedo. And this has had an impact on surface temperature biases and therefore the sensible heat flux. But we know that the changes we've made are fairly robust and based on observations. So we can justify, I guess, a degradation in the model performance for that particular variable, because we know that the science we put in is actually more correct. And it could be that there's other biases in there that we've basically double accounted for. So it's a balance between weighing up whether the science changes that we've added are correct and whether the actual results through the ranking is justifiable, and actually we can use that going forward. So overall, the rank is actually better. So we've gone with this configuration, and this is the configuration we're going to use going forward. So this is just a summary of the kind of process we've gone on since then. So the new science changes that users have been working on have basically submitted to us via a ticketing system, and they run the individual benchmark tests themselves and have to demonstrate to the committee the improvements to the configuration. So the configuration manager, which is me, then packages up all these science changes and then puts it into the package that we've seen in these results. So that basically utilizes benchmarking at several different levels. So future outcomes, so where are we going to go from here? So the configurations we've got for the standalone JULES are now chilled, and we're waiting for official sign-off, and those can go to the community to be used as kind of the next cutting-edge configurations that the users can use for going forward. We hope that we can set up a new kind of configuration cycle where we do this on sort of like a 2-year basis. So then we can pull through new science from the community through the standalone community, but also through the coupled JULES system community as well. We also aim to have a basket of benchmarking metrics, and not just use me.org, but have other tools and things available as well. So the evaluation of models is still a valuable tool, but benchmarking is basically fundamental for generating new configurations going forward. We hope that we can use this to target challenges in land modelling in the future. So I shall just leave that there. So that's my basket. Thank you.
If you're sort of taking the average of the rankings, that means things we usually use like RMSE are just considered equally with things we can barely remember like ketosis. Do you think that's reasonable, or?
Probably not, I guess, but I mean there is scope to weight those, the value of those ones, I think, in going forward. I think there are new methods that have been brought in by GAB as well to do the ranking slightly differently and actually have some kind of weighting between the ranks. So you don't just kind of have a value of 1, 2, 3, 4, 5. It's kind of the distance between the ranks is actually.
So have you've also, I guess you've also done this with more conventional. Do more conventional just RMSE and the traditional things give the same order of between the configurations?
So what do you mean exactly?
Well, does the GAL9 also come out best in other tests?
Outside of the standalone JULES? I mean, GAL9 has been tested with standalone JULES, and yes, it is the best, I suppose, has the best science in it as it stands. I mean, it's also been tested within the coupled system as well, and that went through quite a rigorous testing process as well. So, does that answer your question?
Yeah, I'm thinking of the case where you have two parameterizations, both of which have errors in them. You fix one of them, and the global metrics are worse because one parameterization was positively biased, the other one was negatively biased. You fixed one, and now your system as a whole is worse, right? I was wondering, like, in your loop of defining if something gets the seal of approval, anywhere in there does theoretical foundations for the changes, is that included? Because if you're relying on metrics alone, then the situation where you actually made an improvement to a parameterization is on a better theoretical foundation, but your benchmarking metrics could potentially have gotten worse.
Yeah, so similar to what happened with the sensible heat flux, you mean?
Yeah.
Yeah, I mean, I think this is the first time we've really gone through this loop, so we're still kind of learning as to how that's going to, I suppose, evolve over time. And in the case of the sensible heat flux, I think we've accepted that we know exactly that the science is legitimate science. The observations have been used to inform the parameters, but there's clearly some sort of fundamental bias going on already in the system. So I think it's almost a learning process, really, that you have to be aware of that and say move on and see what happens in the next configuration. But we're essentially trying to end up with the best scientific configuration that has the best, I suppose, scientific grounding in it. Whether that in the next iteration of developing these configurations we actually end up with a better result, that's probably the way that we do it going forward, I think. So.
Last question, Aidan.
Sorry, is there any way that you take into account, say you have new science and it brings in more parameters, that you say it was worth adding more parameters to the model? Like, you're in danger of over-parameterizing. Where does that, is there some way you can take account of that?
Take account?
Well, I mean, was it worth adding 3 more parameters because you got a slight improvement, but maybe that's not a good idea? Like,
yeah, I guess it's come down to the balance of actually how much actually improves the model, whether it's overall best for the whole system. I mean, I think if you're talking a few parameters, I mean, that's happened quite frequently in some of the schemes that we're using. So if that does have a positive impact on the fluxes, I mean, it's obviously this is limited. At the moment, we are only looking at the modest surface fluxes. There are other things that other benchmarks we consider. So, I mean, if those parameters come in a different different space, different parameterization within JULES, then you might consider actually adding different benchmarks as well. So more specific benchmarks that are geared up for that particular process, rather than just relying on the six fluxes that I'm using at the moment. So I think that's probably where you'd actually put your effort instead.
Thanks again, Heather.